Welcome, everybody, once more to the official IAU G2 online conference series. This is about massive star as usual, and this will be the last seminar of the season before the summer break in the northern hemisphere. And today we have as a speaker Jakub Klencki, who is presently an ESO fellow in Garching, but very soon will be moving to MPI in Munich. So a very long trip to change the place. And I want to warmly thank Jakub for having accepted the invitation of the IAU G2 Commission, which, as you probably know, is presently in the process of being renovated after 3 years. And in this regard, I would like to also thank Nidia Morel, Fabrice Martin, and especially our former president, Nicole San Luis, for all the work done in these previous years. And welcome the new members, Aida Wolford, Andrea Sander, and Takashi Morija, and also I see Lida is here as will be our next president. So it's going to be a very nice time with the new commission. But let's go back to Jakub, and I want to make a brief introduction. He did his bachelor and master studies in the University of Warsaw in Poland. And after that, he moved to the Netherlands and did the PhD in the Radboud University under the supervision of Gijs Nellemans, Alina Istrate, and Onno Pols. He finished in 2021, so it's quite young. And I can say that his research has been mainly focused on the evolution of massive stars, particularly those living in closed binary systems. And his work is mainly computational and based on the combination of detailed stellar evolution computations and rapid population synthesis calculation that allow to model the global properties of massive star population. He's particularly interested in the formation of gravitational wave sources, what is very good because we will need a lot of people thinking about how we understand this new observation provided by the LIGO and Virgo interferometers. But he also liked to investigate many other aspects of stellar and binary evolution, such as mass transfer, common envelope evolution, compact objects, X-ray binaries, stellar interiors, strip stars, and other processes happening during the evolution of single and binary stars. So basically, this is all I wanted to do, all I wanted to say. And thank you very much once more, Jakub, for accepting our invitation. And the floor is yours whenever you want.
Well, thank you so much. I wasn't expecting such a nice introduction. I'm not sure if I can live up to this, but I'll try. I hope you can see my slides. Please let me know if not. But yes, indeed, today I'll talk about gravitational wave astronomy in the context of what we can do for stellar astrophysics. And this is the gravitational wave astrophysics is a pretty wide field. So just to focus us, the sources that I will be talking about are specifically merging pairs of black holes and neutron stars. So the sources that we can currently detect since late 2015 with the LIGO, Virgo, and now CAGRA interferometers. And so for a bit of context of where we stand, this is a state of the detections of those mergers with the masses shown on the y-axis, and the x-axis has no meaning. And in most of the events detected so far, we have nearly 100 reported in the latest catalog, are mergers of binary black holes. And there's a few sources containing a neutron star merger as well. And those are very nice because the neutron stars can provide us with an electromagnetic counterpart that we can hopefully detect. Well, we have one detection at least. And so most of the events detected so far actually come from the latest observing run, or the latest finished observing run, 03, as shown as this diagram here. And this is because with each run, there is an upgrade to the sensitivity of the detectors. 01 or 3 or 4, and now we have 04. And so you can see that the distance in the universe that we are probing is increasing, meaning we are seeing a bigger volume, meaning that the rate of the detections is increasing with every upgrade. Additionally, with the Kagra detector joining the frame, the localization of the sources will hopefully get much better, meaning better chance for an electromagnetic counterpart. And so because of those upgrades, the prediction is that this is only kind of really the beginning. The number of sources detected in gravitational waves is expected to go into thousands and eventually millions in the next 10 years. And this is already with the present detectors getting better, but also most excitingly with the next generation of detectors such as Einstein Telescope or Cosmic Explorer in the US, which are going to be sensitive to binary black hole mergers, merging even at a very high redshift. You're talking redshifts 10 to 15. And I mean, this is really something extraordinary, having a merger of two black holes basically every second throughout almost entire cosmic history will arguably get up to the stage that with gravitational waves, we would produce this best measured state in the evolution of massive stars across the universe. And so this is very optimistic, but even if this happens, the best challenge, the current challenge right now is how to be ready on the sides of models to interpret this data and to take the best advantage of this. And so this is not easy. But one thing I'd like to point out is that even with the present detectors that only see the redshift of about 1, we're already probing sources that could originate through even the early universe. And this is because even though the evolution of massive stars is a very short-lived phase, and we may form those binaries of two black holes early on in the far universe, the timescale from the formation of two black holes until they coalesce and merge can be any long we want. And so this means that we could already be sensitive to sources that actually originate from some of the first galaxies, but just take 10 billion years to merge. And the key element in this picture of interpreting the population that we see is what we call formation channels. So how we go from the initial state, which is usually massive stars, to the pair of two neutron stars, those two black holes that are close enough that they will merge within the age of the universe. And so there's lots of formation channels that have been proposed, and there's a lot of work going on them. We could broadly divide them into channels known as isolated evolution of binaries or triples, in which the two massive stars or a triple is thought to evolve in isolation. There is a bunch of channels that we can label as dynamical channels, where the tasks of bringing two black holes or neutron stars together is really helped by dynamical interactions that are common in some places in the universe, such as global clusters and nuclear star clusters. And there are other ideas for the formation of those sources. For instance, some of the black holes that we see could actually be the primordial black holes that were formed early in the universe after from some of the density fluctuations left during the inflation. And so this paints a very exciting picture because those channels operate in different environments. Some of those environments are really hard to probe in other ways, such as centers of galaxies at far redshifts, for instance. And so this is very nice, but it also means that what the population we observe is quite complex, and it's not so easy to interpret this. And so this is the challenge that we really are facing, that we could be seeing contribution from simultaneously many different channels, and the observed sources are potentially quite similar. And so what this quite complicated figure is showing is sort of at the level of our ignorance and for particular classes of channels, where the x-axis is showing the predicted merger rates of binary black holes from different papers, color-coded to different formation channels. So we have isolated binary evolution that I will talk more about in a minute. We have some dynamical channels over here. And so we can see that the predictions span multiple orders of magnitude. And now we are trying to add those populations, those uncertain populations together to create something that we potentially see. So you can see how this is a really complex challenge. And so one hope is that this will get better when we get more data, because eventually we'll get into sort of data-driven era of gravitational waves, when we'll have so many detections that hopefully this will help us to identify subpopulations by the fact that there are some peaks in the distributions, by the fact that there are some correlations, or perhaps some of the sources come preferentially from the redshifts where the global clusters were forming, and so on. So we can hope that data will help, and that maybe we're going to be able to separate subpopulations and maybe assign them to different formation channels. But I think even then, even if we were able to say precisely how many black holes and neutron stars were coming from stars throughout the cosmic history, we still have this challenge of how to use this great data to be able to learn about stars, about massive evolution, about the role of stars in the universe. And I think the key element here is really to get a good understanding of the formation channel so that we could use that as a measuring device of stellar evolution seen through gravitational wave sources. And so this is what I'm going to mostly talk about today. Now, when we think about the evolution of massive binaries, we have three main formation channels that have been proposed and discussed in literature. Chemically homogeneous evolution, common envelope channel, and stable mass transfer. Now, every channel needs to overcome the separation problem. The problem is that for a pair of black holes or neutron stars to merge, they really need to be very close to one another so that the gravitational wave emission will spiral in the binary and merge it. And so we are talking about separations of a few solar radii up to maybe 20, 30, 40 for the most massive black holes. Now, massive stars that we think are progenitors of most of these, they tend to often become much bigger when they're blue, yellow, red supergiants. And so we need to somehow work around this. And different channels have different ways to do this. So in the chemically homogeneous evolution channel, the idea is that the stars really get very big when we have when they have a core that is contracting and an envelope that is expanding. And this happens because we have a composition gradient. Yeah, part of the core is being enriched in helium and it's contracting, whereas the part that's actually not burning and has a hydrogen envelope is expanding. So the way to avoid this would be to mix throughout the entire star so that the composition is chemically homogeneous, as the title suggests. And so it was proposed that this could happen in very short period binaries where the two stars are tidally locked to the orbit, so they rotate very fast with the orbital frequency. And when the stars rotate quickly, there is a mixing induced by this rotation. And so that this way, the helium produced in the center could be distributed through the entire star. And so essentially, we have this Wolf-Rayet star pretty early on, and we could avoid stars expanding to become giants. So this means that we could start the evolution from short orbital periods already. And so this gives us a pretty well-defined parameter space for the chemically homogeneous evolution to occur. And we are talking about periods of a few days. So in the way to think about it, if we see gravitational wave sources from this channel, this means that we kind of know what sort of binaries we are looking at. We have a handle on the progenitors. What we need for this is high masses and also low metallicity to prevent wind slowing the spin up of stars, slowing the rotation of stars. And so the predictions from the chemically homogeneous evolution is that they would produce quite massive pairs of black holes. And in the gravitational wave community, they use this quantity that's more directly measured rather than the mass, which is the chirp mass. It's a combination of two masses. And the prediction from chemical homogeneous evolution that most of those sources would be for chirp masses about 30 or so. And this diagram that's showing here is the measurement reported from the latest population paper by LIGO Virgo. So on the upper panel, you can see the chirp masses measured for individual events, as well as the combined posterior. In the bottom panel, you can see the attempt at inferring what the underlying population is. And so when you look at this, the chirp masses that we see, go to a few solar masses up to, a few tens. But if we think that chemical homogeneous evolution mostly produces those with 30 or above, then we are looking at the subpopulation of the current, what we currently detect. But this is fine. Maybe this will lead us or help us to identify this in the future. We're having more data that, there is this feature that could be associated with chemical homogeneous evolution. Okay, so we can start, filling this diagram. We have three channels. We can say that the gravitational wave sources are probably the more massive of black holes, and they are potentially also more likely to be spinning than not, because we have a lot of angular momentum within the star throughout the entire evolution. This is quite uncertain because the winds can slow it down even late in the evolution, but as a ballpark, this is maybe our prediction. And maybe with these channels, we would be looking at really short orbits of two O-type stars that they quite quickly transition to become Wolf-Rayets during their evolution. All right, let's move to the other channel, the common envelope evolution. So here the idea is that we have two massive stars that now go through the usual giant stages, which means that they will interact through mass transfer. And we can show those evolutionary diagrams, and we can assign different evolutionary stages that we may see or not. And particularly key are the phases of interaction when you transfer mass from one star to the other. And then once one of the black holes or neutron stars is formed, this is when the common envelope happens, when we have the reverse mass transfer. So the idea of the common envelope is that if you have a binary of an expanding giant and a compact object companion in this case, it might be that the giant is expanding so much that it essentially becomes as big as the orbit. And that means that this companion compact object will start to move throughout the envelope of the giant star. And as it's moving through the medium of gas, it's experiencing a drag force, and that drag force is slowing it down, or rather it's causing this companion to spiral in throughout the envelope. And this spiraling reduces the orbit. It can reduce the orbital separation by orders of magnitude. So this is kind of a natural expectation that this process may be needed or certainly help in producing those short period orbits that we want for gravitational wave sources. And this in spiral also puts energy into the envelope. And if you do something like this, then the envelope usually expands. And so the idea is that if you put enough energy into this expanding envelope, then you can eject it to infinity and stop the in spiral. Now, there's an observational counterpart to this process. It's not pure theory. We know that sometimes stars strongly interact and even merge. And this is associated with transients. And they're sort of intermediate luminosity transients, not quite as bright as supernovae. And they're also very red. And so they've been called luminous red novae. And the fact that they come from stellar mergers is the smoking gun signature of that was an observation of a binary that was actually had its orbital period decline so quickly that we were able to measure this. And then eventually at some point, we had a transient. There was some brightening before the transient itself, and we think this might be coming through the outflows from the binary that happened during the mass transfer, but before it becomes unstable and we reach the common envelope phase. And this initial brightening is actually maybe something that we could look for to find so-called precursors of stellar mergers of common envelope events and identify candidates for future transients, for future luminous red novae. But then eventually, once the star plunges in or really starts this in spiral in a dynamical phase, this is where we get the transient. And so it's not necessarily so easy to find all of those, for instance, in the galaxy. And this is because we think that a lot of the luminous red novae will really be quite red, only potentially clear in the infrared surveys. And so some of the efforts that are going on now is to move to the infrared and really find if there is a bigger underlying population. Other than that, we have a few luminous red novae that we think come from massive stars. They're mostly extragalactic sources, but it's not quite enough to have a good observational handle on the population of the common envelope happening in massive binaries. Now, after the ejection of the envelope, what we may see is a planetary nebulae with a hot central star, but we don't actually see any post-common envelope systems like this in the massive star regime, at least not yet. We may come back to this later. And so I was painting this picture that we have the envelope, we put energy into it, it expands, and then we can eject it. And so if that doesn't happen, and it shouldn't always happen, I mean, I can throw a rock into the atmosphere of the Earth, the envelope of the Earth, and that usually, hopefully, shouldn't unbind our atmosphere. And so if I throw a body that's much smaller than this envelope, then the amount of energy I put into the envelope probably doesn't unbind this. And so there is some limit. And we can ask a question of for which binaries this spiraling companion puts enough energy into the envelope to eject it and to stop the in spiral. And this is something we did in the context of gravitational wave sources, specifically in the black hole binaries. And so we were looking at what are the binding energies of massive stars that we think may become black holes or neutron stars. We're trying to be optimistic to say that in this process of in spiral, really all the energy that we have at our disposal is being used to create kinetic energy of this envelope. And so there is no radiative losses from the surface, which is not quite true, and that the envelope is precisely accelerated to this escape velocity with no extra outflows. And so with those assumptions, we found that, well, basically, if we think about what stars do we need to initiate this common envelope, what massive stars, those massive stars need to be red supergiants. And this is because red supergiants have convective outer envelope, and those envelopes are much less gravitationally bound than the radiative envelope that massive star has during most of its evolution. So we really need the wait for the massive star to expand to red supergiant phase for this common envelope evolution to be likely. Okay, this is nice. We have some red supergiants, and this is probably somewhat outdated sample of red supergiants in the SMC. But what observationally we find is that there is no red supergiants above this limit. Here this limit is plotted at 5.6 luminosities, which for those tracks that are tracks corresponds to initial mass of 35 or something like this, which is quite uncertain. But basically, there is this limit of mass above which we don't see red supergiants, and there is reasons to believe that massive stars above a certain mass may never become red supergiants. And if that's true, and if we need those red supergiants for common envelope channel, there may be an upper limit for this channel to work. And so that means it wouldn't work for a good portion of the black holes that we see currently in gravitational waves already, 20, 30, 40 solar mass black holes, that would require more massive stars than the ones we see in the red supergiant population. And so Amadeo Romagnolo, who is finishing his PhD at the Copernicus Center in Warsaw, he's been working on a little bit to quantify those effects in the context of gravitational wave population models. And so what you can see in this diagram is the composition or the collection of, well, this is a result of a gravitational wave population synthesis model. The blue and the green dots are stars that in this model were donors to a common envelope event that led to the gravitational wave source. Now, the vertical lines are showing where we think the stars develop convective envelopes. And we are probably being quite optimistic here. So everything to the right, let's say that those could be red supergiants. And so what you can see is that in many population models, there is lots of stars that initiate common envelope and survive it that we think are really quite far away from having the right envelopes for this to happen. And so there are some reasons why this was used in the models, and I can discuss this later, but we are really trying to, to quantify this effect and see how big of a difference it makes in our predictions of the rates coming from the common envelope channel. All right. One final thing for the common envelope I'd like to discuss is I think the challenge that we have now, and that there's more and more work being, focused on, it's really what is the separations, the final orbital separations that the common envelope can produce. Now, this exact value of the separation is very important for gravitational wave sources because the delay times scale with the separation to the power of 4. So it's important for whether the gravitational wave sources we see are from the local galaxies or for long delay times, whether they come from some of the most distant galaxies in the universe. And the problem with the common envelope is that, well, we don't have a clear signature of a post-common envelope system from massive stars. So we don't know what those separations could be. In terms of numerical simulations, which is what I'm showing here, those simulations can probe the inspiral, the dynamical phase of it. But towards the end of the inspiral, when the orbit is already very short, this is where our predictions are not really robust yet. And the reason is that in the numerical 3D simulations, we have to replace the core with a particle, sync particle, and there is some choice in that. We are not capturing how the core is responding to the loss of the envelope. So we can make predictions. We can see how our predictions depend on the cuts that we make. But getting a robust value, I think, is quite challenging. And another problem is here that, and after we had this common envelope phase and we've ejected lots of mass, potentially a significant part of this mass may actually still be bound and orbiting in binary in the form of a circumbinary disk. And having a circumbinary disk around your orbit will have an impact on the orbital separation even after the common envelope has been ejected. If we accrete mass from the disk, that could potentially give us more angular momentum into the orbit, so the orbit would be expanding. But on the other hand, there is a counteracting effect of tidal torques from the disk that could lead the orbit to shrink and potentially even merge before we form the second black hole or neutron star. And this is an effect that was, I don't quite have a figure, I thought I do. But this is an effect that was looked at by Dan Bay and others from Heidelberg recently. And then they found that depending on the mass and the lifetime of the disk, this can completely change the separation of the binary after the common envelope. So this might actually be this crucial phase of interaction that really defines the properties of gravitational wave source that we have a pretty poor handle on. I mean, we don't know the properties of those disks and their lifetimes and so on. And actually, quite similar challenge is happening for a different formation channel for binary black holes. This is a channel which thinks about how some of the binary black holes may be evolving in the disks of active galactic nuclei. And in AGN disks, what's happening is you have this endless reservoir of matter from the disk that you can accrete onto the binary. So this effect is even amplified. And the results from numerical simulations are really not converging at the moment. So we are pretty far from the consensus of what the effect of this process is on the final orbits, on their separations, and as well as eccentricities. All right, I was rambling a bit about the common envelope, but basically, if we try to summarize it briefly, we think that this channel certainly works for double neutron star mergers. We think that this is the main channel. Should also work for low mass black holes. There are some question marks whether it can work for more massive black holes too. And the progenitor stars that we probe with this would be red supergiants, and they live in binaries that before would look like potential big X-ray binaries. Okay, and finally, we have a stable mass transfer channel. So here the idea is that we don't have the common envelope. It's a very similar evolution, except that the mass transfer stays stable during this phase with a compact object accretor. So observationally, this phase would look like a very high luminosity X-ray binary system, high mass X-ray binary system, or depending on the viewing angle, it could be an ultra-luminous X-ray source, ULX. Now, you can ask why, okay, you said we need small separations and the common envelope gives us small separations. So why should this work without common envelope? And so basically the trick is that even if the mass transfer is stable, if you're transferring a mass from a more massive star to a less massive accretor, then the orbit is also shrinking. It's not shrinking as much as during common envelope, but if you start from a smaller orbit to begin with, then you can reach similar final separations. And so this is what this figure is trying to illustrate when you have an SMT, so stable mass transfer evolution, starting from stars which have a smaller radius of a few tenths of radius. So we're talking about orbits of, not hundreds of days, but a few tenths of days, for instance, or a few days. And the orbit is shrinking, not as dramatically as during common envelope evolution, but you still can end up with a narrow orbit binary with a delay time, approximate delay time that is within the age of the universe. Okay, so this can work. And this is the channel that I would say is gaining the most popularity recently. And now there are two lines for the stable mass transfer channel, the yellow and the blue one. And the difference here, that is the assumption about with the angular momentum budget during the stable mass transfer phase. So you can picture that what we are seeing is this high mass X-ray binary where we have a star that's feeding mass at a supercritical rate to the compact object companion. And so quite likely the neutron star black hole is not able to accrete most of this mass, and most of this mass is lost from the system. And it can be lost in various ways. We see the indication of those ways in the observations of systems such as SS433 here. This is an artist impression, but I thought it was quite nice. And what it is showing is the jets that we actually see in X-rays and gamma as well. And this jet is losing a lot of mass, but there are also much slower outflows that are more in the equatorial plane, coming from disk. Those are disk winds and maybe just outflows from the matter that doesn't quite form disks. And people are trying to make models for all this. But we really don't quite know how much mass is being ejected from the system, from the jet, or from a slow outflow. And all of this matters because if something is slowly outflowing from your system, it's going to interact with the orbit for longer. It's going to have more angular momentum carried away from the system. And so if you have more what we often call L2 outflows, then you lose more angular momentum, so your orbit shrinks more. And this is this blue line here. And this can have a strong effect on the delay time. As you can see, these are 2 orders of magnitude difference. And I'm not making extreme assumptions, really. But even with that, that was one example here, one particular star. We can try to think about, okay, what's the population? What sort of orbits do we need for this channel to work? And so this diagram here is showing results from simulations of binaries with MESA, of a massive star with a black hole companion. On the x-axis is the initial mass ratio. So the black hole is fixed, it's always 10 solar masses, and the mass of the star is changing from 20 here to 100 on the left, actually. And on the y-axis is the initial orbital period. And then those are all individual models, and they're colored according to the outcome. So in the yellow, there are systems that went through stable mass transfer, but formed system that is too wide to emerge as a gravitational wave source. And the gray, this is the other extreme. Those are systems that were pretty small to begin with. And so this mass transfer is actually leading to a situation where the orbit shrinks too much. The mass transfer becomes unstable, and this black hole companion sinks into the giant donor star. And we think that this could either lead to the disruption of a star in a transient, or potentially to the formation of a somewhat longer-lived quasi-star, a Thornton object that we haven't quite found yet. And then in the middle is this sweet middle ground where we shrink the orbit a lot, so that we create a small short period system, but not quite too much, so it stays stable. And we can create the binary of two black holes that merge as gravitational wave sources. And in top, by the way, here in the red is the systems where the mass transfer is initiated from a convective envelope star, a red supergiant. And we think that this leads to common envelope evolution. So that other channel I was discussing before. Now, one thing to take away from this figure is that there is, we have this stripe in the parameter space. We expect systems to be everywhere, black hole binaries. And so this means probably only a small fraction of the black hole class star systems that we know about will eventually become gravitational wave sources. And I'm talking about systems where the black hole is found in an X-ray quiet system, when it's not really transferring mass to its star companion, as well as X-ray binaries with black holes. And then a small percentage of those probably becomes gravitational wave sources. So I was talking before about this uncertainty associated with where the mass is being lost with the system, the angular momentum budget. And so depending on this assumption, this exact parameter space for gravitational wave sources will move up and down. If we lose more mass through the L2, if you lose more angular momentum, then you can start with a wider orbit to begin with to still produce a narrow system gravitational wave source. But we can also ask a question, not only which orbits do we need, but which stars do we need for stable mass transfer channel? Similarly to in the common envelope channel, we said we need red supergiants. So what stars we need here? And so the experiment that was done here is the following. This is a diagram that's showing as a function of the mass of the star, going from 10 to 100, and the radius at which, and the radius at which this star initiates mass transfer. So in the bottom here, this is a few star radii. This is mass transfer initiated early during the main sequence in the binary. And the other extreme, almost 1,000 radii, this is where the mass transfer is initiated when the star is a red supergiant. It's very big. And so in each point in this diagram, what we did is we ran a set of mass transfer models, and we found for which what's the most extreme mass ratio when the mass transfer is still stable. And the reason we want to find the most extreme mass ratio is that this gives the most orbital shrinkage. And so if we do that in each point, then we can find what's the minimum orbital separation that one can achieve in the stable mass transfer channel from this ULX source. Yeah. And this is now color-coded from 8 solar radii to, well, it's often weighted above 100. And so from those orbital separations, you can then, with some assumptions, deduce what would roughly be the delay time if this star that went through mass transfer collapsed to form the second black hole. So the delay time of a binary black hole system. And this is shown now in the panel on the right. Yeah, the delay time is in log of megayears. So this is 100 megayears in dark blue, going to the age of the universe in yellow. So everything in yellow, those are binaries that take too long to merge. Everything that is not yellow, those are binary black hole mergers or binary black hole systems that will merge, produce gravitational wave source. Okay, so this gives us the progenitors of those sources being in green. Now, the nice thing is that in this experiment, this figure is a bit deformed, I don't know why, but in this experiment, the result doesn't depend much about our assumptions on the angular momentum transport. So as similarly as before, the one on the left is assuming no L2 mass flows during stable mass transfer. The one on the right assumes L2 mass flows. And the result is similar. And the reason for that is this orbital separation that you can achieve through stable mass transfer. This really mostly depends on the star and the structure of the star, rather than what's happening with the mass during mass transfer. And so this may be a useful way to trying to connect gravitational wave sources and their delay times to actual progenitor stars. And so this is what we're trying to do. So now with this outcome, what would be the gravitational wave sources? We can look at this and we ask, okay, some stars don't seem to be able to produce gravitational wave sources for a stable mass transfer channel. What's wrong with them? So the yellow regions, the ones on top, well, those are convective envelope stars, so they are prone to go through common envelope evolution rather than stable mass transfer channel. It's a different channel, essentially. Okay, that's fine. Now, the stars on the left are stars that rapidly expand at the end of the main sequence, which means we have a massive star, it depleted hydrogen, it's a terminal main sequence, the core contracts and the envelope expands to become a red supergiant on a thermal timescale. So those stars cross the HRD very quickly, and we basically wouldn't observe them as blue supergiants. Now, if those stars interact during mass transfer, they're somewhat more prone to be unstable. And in this mass range, they're not stable in mass ratios that are extreme enough for the formation of LIGO Virgo sources. But what I think is very interesting is the stars on the right. Those are the most massive stars that would maybe produce the most massive black holes. The mass transfer is actually stable for pretty extreme mass ratios of 8 or so even, but they still don't shrink the orbit so much. And the reason is those stars are quite enriched in helium already from the main sequence. The more massive the star, the bigger the convective core. And so there is less hydrogen left in the envelope. And so what happens in those stars is that they lose less mass during mass transfer. And because they lose less mass, they shrink the orbit less. Or the other way to think about it is you initiate mass transfer, you strip a relatively small fraction of the star, and the star detaches from the mass transfer already, while this orbit is still quite wide. And so the problem of those stars in a way is that they're too mixed with helium already throughout the revolution, which is something we didn't expect. Now, the best case donors for this, or the ones that produce the smallest systems that merge the most quickly, are core helium burning yellow supergiants, it turns out. So the stars that are not convective, they have radiative envelopes, and also the stars that are the most evolved. They have the smallest cores, and they're the most stable in mass transfer and forming those narrow systems. Now, the possible consequence of this, if you form the shortest delay times from the systems that interact in still pretty wide binaries, such as yellow supergiants, if those were really to exist indeed, they would be forming gravitational wave sources from pretty extreme mass ratios, because you need to shrink the orbit quite a lot from a yellow supergiant to a few stellar radii, which would mean that the shortest delay times from stable mass transfer would also be associated with unequal mass ratios binary black holes. And this is what this prediction is showing, where there's delay time on the y-axis, and the shortest delay times that may be achievable come in systems that are also unequal mass ratios. And this is an example of a predicted correlation or anti-correlation that we are looking for in different channels to really try to identify how those subpopulations from different subchannels will look like, so we could then, in this data-driven era that I was quite optimistic about, so that we could really separate the populations. All right, so now I talked about all the channels. In summary, for stable mass transfer, we think it probably can work for all the others, but there is maybe a limit that it's maybe difficult to make it work for some of the most massive stars that don't quite have enough envelope to lose. But I think we're still trying to understand this. But one thing especially thinking about progenitors we see, I'd like to stress at the end of this talk now, is that we're all making quite a big simplification here. And that this key phase of mass transfer, whether a stable or unstable common envelope, this mass transfer is initiated from mass gainer star. And this is something that we are presently pretty much ignoring in all the gravitational wave population models. This is only pointed out as a problem by Matteo Renzo, especially in his 2023 paper. And there are some models being in preparation for detailed binary evolution models that take account the effect of accretion self-consistently in making a prediction for gravitational wave sources. But this is really something that we are doing for the first time, learning what the result would be. But I think this is something we definitely keep in mind. And so if you want to account for the mass gainers and the fact that the mass gainer star is maybe not the normal star, if you dump a significant amount of mass on it, if you want to learn about mass gainers, I think the best way to do this is to go before in this channel, to stars to where the mass was being gained. And this is after the first phase of mass transfer. This is the mass gainer. So those are post-interaction binaries that we're actually finding more and more frequently now. And so this is a figure from a paper that appeared on the arXiv yesterday. I think it's a study led by Varsha Ramachandran, and it's showing a collection of stripped stars found in post-interaction binaries. And so in the blue, you can see subdwarfs and hot stripped stars. The hot stripped stars that you need the UV photometry to really find well and characterize well. This is because they're so hot, they emit most of the light in UV. So quite often the hot stripped stars would be outshined by their companion on the main sequence. But we also have this population of what we sometimes call puffed up stripped stars or partially stripped stars, which are not quite as hot. In fact, they may be overlapping with the main sequence. So at the face value, they may look like a normal main sequence star. But what we think the interpretation of those stars is that they are actually still contracting or all the way to become hot stripped stars. And this is what those evolutionary tracks in the background are showing, where we had a normal evolution of the star, it expands, the mass loser goes into mass transfer. At the end of the mass transfer, it begins to contract. And before it becomes blue, it's transitioning from this region. And this is maybe when we're seeing as a partially stripped stars. And so the properties of those partially stripped stars in binaries are that they are strongly enriched in nitrogen. They show clear indication of CNO burning because we lost a lot of mass. They have a very high luminosity to mass ratio because you lose a lot of mass, but you don't lose luminosity. And they also have somewhat enhanced mass loss compared to similar stars on the main sequence. And so those properties maybe help us to identify more candidates in the current surveys. And in fact, the prediction is that perhaps we're just seeing the tip of the iceberg. So with a student, Debashish Dutta, what we did is we tried to estimate how many of those partially stripped stars do we expect to see. Now, the base number prediction is that roughly 1% of stars that overlap with main sequence could in fact be those cool stripped stars that are contracting. This may mean hundreds of binaries still to be discovered in the big spectroscopic samples, tens of hundreds. And the key is to really identify the stars that maybe show indication of being good candidates for a post-interaction system. Either something that's enriched, nitrogen enriched, and has low mass, low gravity, or something that has a BE star or OE star companion, so a rapidly rotating star that has all the indication to be a past mass gainer. And the one thing that I think is quite puzzling is that we are already seeing so many of those. So in this box here, we have 4 stars, partially stripped stars. 3 of them are from the SMC. Now, from the model we did with Debashish, the population model is quite uncertain, but let's say we predict a few stars there. But this is assuming that we looked at the entire SMC. But this is not the case. Those 3 stars were found without a systematic search yet. And there's a good chance to believe that there is many more out there. And if this is true, then this maybe mean that for some reason, these partially stripped stars are longer lived or more common than the standard evolution models predict. And we have some ideas for those, but I don't quite have time to go over this. So just before I finish, I want to So to flash those couple of examples of what we think are some of the quick questions that we want to answer for mass gainers, to understand mass gainer stars, to then put them back into gravitational wave source formation models. And those are questions such as how much masses and angular momentum is being accreted in the mass gainer in those post-interaction binaries. What is the internal structure of mass gainers? How much the core grows together with the envelope growth? How are on the inside, the mass gainers different from normal stars? People are trying to figure out a way to do this astroseismology, which could give us a way to really look inside the star. And there's good reasons to believe that the different structure of mass gainers will have a strong impact on the mass transfer properties in X-ray binaries and gravitational wave source progenitors. And finally, it would be nice to know, well, we have great work, we have great detections of magnetic fields in stars that we think are mergers. It would be great to know if something similar and how often could be happening in stars that haven't merged, but have just accreted some amount of mass. Okay, and then really, looking back, there are many ideas of what we can do with mass gainers, post-interaction binaries, massive stars in general. And I think it's good to keep this picture in mind that this gravitational wave source population is very complex. I was just talking about one branch of channels. There are different channels with very different challenges. And the models built to interpret the population are really quite complex. So our understanding of massive stars is a part of it. It's probably a key part of those models, but it's not the only part. And so we need to keep this perspective of understanding which of our uncertainties, which of the behavior of massive stars and binaries is really key for the formation of gravitational wave sources, to be able to focus our efforts in the right spot and to really turn this gravitational wave machinery into a measuring device for massive stars, which is something that I think we hope to do. And with that, I'll just leave you with my summary that the universe is loud in gravitational waves. There's a lot of hope. There's lots of challenges as well. And mass transfer is one of those uncertainties that I like to think about and work about the most. I don't know. If I still have 2 minutes, I can flash back to the initial question, whether the gravitational wave astronomy can be the renaissance of stellar astrophysics. And so we can look at this that, well, yes, of course, if we measure black holes, neutron stars throughout the entire cosmic history, I mean, surely we can learn many new things that we haven't known before. And somebody may say, well, not really, because we really just see end products of massive star evolution. There's so many uncertainties on the way. We can learn more about massive stars through other methods, through actually observing massive star populations. That's a more pessimistic approach. But I think to end on a good note, we can say that even if that's true, we would still learn more about massive stars because of the motivation and the funding that comes from gravitational wave astronomy, to the amazing research by amazing star astronomers. And with that, I'd like to end. Thank you.
Okay, thank you very much, Jakub, for this very extensive and interesting overview of the topics. I have to admit that I've learned many things I didn't know before, so thank you for the time preparing all this nice seminar. Time for questions. Rafael, please.
Yeah, hopefully you can hear me now. Okay.
Yes.
Can you go back to your common envelope plot with the HR diagram?
Sure.
So I think this was for SMC models.
The models, yeah. Oh, I'm sorry, but my fantastic software is lagging. But it's here. Okay.
Okay. Very nice talk. Very clear. I also learned a lot. My interest is, okay, so have you considered lower metallicity models? Because in some sense, this is low metallicity, but maybe could still be a lower.
Yeah.
And then even lower metallicity, you would still have hydrogen-rich material in, let's say, 85 solar mass star, and then whether you consider that at even lower metallicity, you could still have common envelope ejection because mass loss was weaker at even lower metallicity.
Yeah, that's a great question. So we went all the way up to 1% solar. And as you know very well, in 1D stellar models, we can produce red supergiants at low metallicity. So we can extend our models all the way up to here. Maybe we don't need all the way up here, but basically we can produce outer convective envelopes from stars of 80 solar masses. Now there's two questions. One question is, should we see them in some of the more distant but meteor pool nearby galaxies? I mean, there is the empirical limit on the masses of red supergiants. In the metallicity range that doesn't go to 1%, but still some metallicity range seems to be metallicity independent. So there's a question whether we have those red supergiants, very luminous red supergiants only in the models, or whether they appear in nature as well. And I think understanding the mass loss during the LBV regime may be one of the keys here. But the other thing I think it's an interesting question is when massive stars expand to be a red supergiant. If you go to very low metallicity models, or especially POP3 star models, some of those expand to the red supergiant stage only after the end of core helium burning, right? Which means for these very massive stars that we have maybe a couple of thousand years for the common envelope phase. And it's not quite certain if this is enough. The dynamical and spiral phase itself is very short soon, but this is not the only phase. Before the common envelope starts, we have this phase of mass transfer that's not quite stable yet. And then even after most of the envelope was ejected, the final separation may set up during this slower self-regulated phase that lasts longer. So I think it's also a good question to wonder about if for the stars that expand late during their evolution, if there is enough time for a full interaction to happen before they collapse. I don't know if that makes sense.
I have a question myself related to this one posed by Rafael. I was going to ask you, maybe you will need another 10 minutes or 15 minutes of seminar, but what is the impact of metallicity in the three different channels that you have mentioned? Because obviously, for example, I was thinking in the first one, where you have the closed binaries, for chemical homogeneous evolution, you need fast rotation. And I assume that low metallicity would imply, or normally say that low metallicity, you have less winds, so less angular momentum loss, so you allow the star to spin faster. But if the two stars are tied together, then the rotation is not going to be too fast, even in this case. So I was wondering if you have an idea, or you could explain us briefly how is the impact, or what is known about the impact of metallicity in the different channels. You already mentioned something for this one, but for the others?
So I think this is a question that people are really trying to answer in the gravitational wave source population community. Because it would be very useful to know the relation between metallicity and the formation efficiency of all of those channels. The reason it's useful, it's not only physics of stars, but also if we want to understand the population, the metallicity changes as a function of redshift. Maybe we know roughly how. If we know the formation efficiency as a function of redshift for those sources too, maybe we can use that information to disentangle, the population that we see and help in interpretation of the origin. So this is a big question, I think. And I think the key element that really defines this relation in models, and by the way, what models find is this low metallicity is important for all the channels. And I think the key element that does this is the core collapse. That in most of our assumptions that we put, if you want to form black holes, and especially black holes with low natal kicks, and this is something I didn't talk about, but we don't want those natal kicks because we don't want to disrupt the binaries. Then usually models tell us of which stars collapse to black holes is that it's better to have a more massive core. And this is where we go to lower metallicity, because we say, okay, low metallicity, we have less mass loss through winds. So this is where we get the most massive cores, progenitors of the most massive black holes that collapse and direct collapse. So I think actually this is why different channels show a similar result in our predictions.
Okay.
But this is quite, this is really model based, and a lot of our understanding of the winds that go into this is based on the extrapolation of our understanding of winds in the higher metallicity regime than less than 10% solar. So the result is important, but just because every model shows this, that low metallicity is important, I don't necessarily think this means it's robust. It may mean that our models are similar but not necessarily correct, if that makes sense. And getting a better handle on the winds as a function of metallicity, it would certainly help there.
Okay, because I think this will have also an impact on at some point we don't know the metallicity of the gravitational wave events, no? For the moment, we
don't.
Yeah, we are just assuming that we see more in farther distances because it's lower metallicity, but not necessarily, no? So maybe it's just a question of a larger volume, and so this is why we are detecting more and more, but not necessarily because we are going to lower metallicity, no?
Yeah. I think having a rate detected as a function of redshift, for instance, which is something people are probably trying to do, is going to help there.
Great. Any other question here? Dietrich?
Yeah, thank you. A really great talk, Jakub. Thank you very much. On the one hand, I have great respect for the fact that you have resisted what must be a temptation to talk about ZLK. But do you have an opinion that you can add? How the ZLK oscillations in triple systems can change a picture? I mean, there are quite a few higher order systems and among the massive stars, not just binaries, at least in the local universe.
Yeah, that's true. So I didn't talk about this at all. And the idea is that we have triple system when the outer tertiary is on an orbit that's inclined to the inner binary orbit, and that causes ZLK oscillations, which causes the inner orbit to become eccentric, which may help in merging the system. And so people have done estimations of this, what the rate could be. And it's usual for other channels, the rate is very uncertain. So we can go from, I'm not sure I know enough on the initial conditions of triples, for instance, to have an educated opinion of which of the rate extremes are more likely. I think that adding a lot of the challenges for isolated binary channels are quite similar to the challenges for triple evolution. So the understanding of how often do we get chemical homogeneous evolution, people thought about it in the context of triples as well. What is the mass transfer stable or unstable in the inner binary of a triple? Some of those questions are the same, which is nice because then we can help each other. And then the interaction of the inner binary with an outer orbit may help to create a gravitational wave source for some systems that otherwise as binaries would be too wide to merge. And actually there are ideas that the help may not only be coming from a third star and a triple, but also, for instance, from a galactic tide. If you put a black hole binary in the galaxy with right potential and let it move in this galaxy for a couple of billion years, then there is the orbit fills the galactic potential, and eccentricity may also be excited, helping in the merger. So this is just to give a hint that there's lots of different ideas being thrown around, which makes it a bigger challenge to build just one population model that takes all of them into account. Pretty much impossible, at least now. I'm sorry for not directly addressing your question, but it's good to bring that up.
No, thank you for your opinion. Very helpful.
Jaime?
Really, really great talk, Jakub. I only have a few dozen of questions, but I'm only gonna make one or maybe two. So did I understand correctly that the more likely, or perhaps the best type of companion in the case of stable mass transfer channel will be yellow supergiants?
The best for the shortest delay times.
Right.
I would say, to be honest, because we don't have mass gainers in our models, that we don't really understand this. I think we are just moving slowly towards having an idea what are the right stars. What seems to be the result that you understand correctly is that the yellow supergiants may be the best stars to create really the narrow systems with a few solar radii, which is comparable to common envelope evolution, actually, those separations. But in this figure, there's lots of stars that are not yellow supergiants. They would produce gravitational wave sources, but long delay times.
Okay, I see. And this this evolutionary stage of the companion, let's say, is at the time of the compact object formation?
Of the time of when the mass transfer starts.
When the mass transfer starts. Okay. But that means, so that means that these yellow supergiants were also, I guess the question is, why are you counting them? I guess the question is, why are you counting them as yellow supergiants and not main sequence stars?
Yeah. So that's a good question, because for most of the evolution, those donors would be main sequence stars.
Yeah.
Another way to phrase this is the right donor is an orbit that's big enough to fit a yellow supergiant, so that when those main sequence stars expand, they would have enough space to expand the yellow supergiant stage before the mass transfer. So I agree, there's different ways to think about it, and I agree we should find the best way to think about it. So I'm happy for the feedback.
I see. Thanks.
For instance, and there was a paper, I think yesterday or maybe today on the archive from Anna O'Grady, thinking about the binary fraction of yellow supergiants, which is something that we don't know very well. That is nice, because that tells us how many binaries are potentially with the right separations to fit the yellow supergiants, maybe be close to interaction. And maybe we can hope to see some of those interactions with yellow supergiants in action.
I see. Can I perhaps make one quick question, Sergio? One more. So does the mass of the compact object or the nature of the compact object have any significant importance here for the formation channels?
Probably yes, but I don't think we understand this to make quantitative predictions. And the reason it probably matters is because, if you have a neutron star with magnetic field, especially, it's going to affect the flow of the materia accrete, whether during common envelope or during stable mass transfer versus black hole. But I don't think, and this would affect, where you lose mass from then, ULX, for instance, or how often do you have a jet during common envelope phase. But those are questions that we don't understand enough, I think, to make a prediction, unfortunately.
I see. Thank you, Jakub.
So I have myself a request and a question. As observer, it would be great if you can also put this information in a HR diagram, because yellow supergiant is a bit ambiguous.
Yeah.
So to know exactly what is the domain we need to look observationally, so that would be great. And then the question is, what is the typical time scale of this first, the evolution of the yellow supergiant and then the mass transfer event? Is something that is expected to be observed, or is very fast and we will only see the effect but not the process?
Yeah, well, good question. I mean, I think the most safe guess and the most traditional guess is that the time scale is thermal time scale of mass transfer, so a couple of thousand years. So quite likely we would not see it. I had a paper in 2022 predicting that in some cases this mass transfer may be lasting for a fraction of a mega-year nuclear timescale, so something longer, meaning we would maybe see some yellow supergiants currently interacting. We see one such system in the Holmberg 1 galaxy, I think. It's an ellipsoidal variable found by Assassin. And maybe there are more in the stars that Anna O'Grady just had a paper on. But I think for those candidates that are from photometry, we need spectroscopic follow-up. Because if there were indeed going for nuclear timescale mass transfer phase here, we should see some. So there would be basically somewhat like algal systems in white binaries or ellipsoidal variables with yellow supergiants. That would be the prediction, yeah. So this is directly the mass transfer phase when they're both stars. This key mass transfer phase that really shrinks the orbit would be during the ULX phase. And then the challenge is that the ULXs are much more rare than just binaries of two stars. So we usually see them very far away, and it's very difficult to observe the donor. Yeah.
So I understand that I was not aware of the paper you mentioned before, but I understand that we will need a specific surveys concentrated in this region to find the objects, no? Because it's not just like by chance that we'll find some of these.
I mean, I think the post-interaction binaries, that I talked a little bit about, I think in a way they're also excellent also for stuff that interacted as a yellow supergiant. Yeah, we are seeing a binary after the mass transfer. And so some of them right after the mass transfer. And so sort of in a way, and they live much longer than the interaction itself. So they're like the right class of objects to understand the interaction happening in different evolutionary stages once we have enough of them. And once we understand the orbits. And this understanding of the orbits can only really happen if we have a population rather than a few systems, because otherwise we're kind of stopped by uncertainties in how the orbit exactly evolves during mass transfer. So the post-interaction binaries are nice, but also knowing more about binary fractions in yellow supergiants, I think, so spectroscopic surveys in that cooler range, that's great too.
Okay, great. Any other question here? If not, let's thank again Jakub for the time and all the information you have provided. And yeah, we are going to stop for a couple of months, but we will be back in September. If I remember correctly, will be Alquiste Bonanos talking about the main results of her ERC project. So I hope you have a nice summer break in the north and enjoy winter in the south. Ciao, ciao.
Thank you. Wow.